When you look up at the night sky, what are you actually seeing? A few thousand stars if you're lucky, maybe a planet or two, the moon on clear nights. But here's what nobody tells you. You're looking at the universe's true face. And 99.999% of what you're seeing is nothing. Pure vacuum. The gaps between everything. And that nothingness might be the most chilling thing in all of existence. Over the next couple of hours, we're going to explore what this vacuum really is, what it does, why it should unsettle you. Because once you understand what's happening in all that darkness, you'll never look at the cosmos the same way again. Let's start with a simple question that has a complicated answer. What is the vacuum of space? Your first instinct is probably to say, it's nothing. The absence of stuff, the gaps where matter isn't. And you'd be partially right, but the reality is far stranger. The vacuum isn't actually vacant. I know that sounds like a contradiction. It is a contradiction, but it's also one of the deepest truths about our universe. When physicists talk about vacuum, they're not describing emptiness in the way you might imagine. They're describing something with properties, something with energy, something that can bend and stretch and ripple like fabric. Here's an analogy we'll use just once, so pay attention. Imagine you have a glass of water. You pour out all the water. The glass is now vacant, right? Not really. It's full of air. Okay, so you put it in a vacuum chamber and pump out all the air molecules. Now it's truly devoid of matter. Or is it? Light is still passing through it. Gravitational fields are still present. Electromagnetic fields permeate it. And even if you could somehow eliminate all of those, quantum mechanics tells us something remarkable would still be there. Virtual particles would be popping in and out of existence. Quantum fluctuations would be rippling through the fabric of reality itself. The vacuum is the baseline state of the universe, and that baseline is far from nothing. Before we dive into the disquieting details, we need to grasp just how much nothingness there is. The scale is almost impossible for human minds to comprehend. Let's start at the smallest level and work our way up. An atom. You probably learnt about these in school. A nucleus in the center with electrons orbiting around it. Simple enough. But here's what they don't emphasize. If you scaled an atom up to the size of a football stadium, the nucleus would be roughly the size of a marble sitting on the 50-yard line. The electrons, tiny specks way up in the nosebleed seats. And everything in between? Vacuum. So even solid matter, the stuff that feels substantial when you touch it, is almost entirely vacant space. Your body? Mostly nothingness. The chair you're sitting on? Mostly gaps. The ground beneath your feet? Mostly vacuum. We're all just clouds of almost nothing that have somehow convinced themselves they're solid. If you removed all the vacuum from your body's atoms, compressing the actual matter with no gaps, you'd become approximately the size of a grain of sand, maybe smaller. Your entire physical structure could fit into a volume you can barely see. So why don't we collapse? Quantum mechanics. The Pauli exclusion principle prevents electrons from occupying the same state, creating quantum pressure that maintains the gaps. And here's something profound. When you touch something, you're not actually making contact. The atoms in your hand and the atoms in the object are repelling each other through electromagnetic forces, maintaining a gap of vacuum between them. At the atomic level, you've never truly touched anything in your life. There's always been vacuum separating you from everything else. The sensation of touch is electromagnetic repulsion across nothingness. The feeling of solidity is quantum pressure maintaining gaps. Now let's zoom out to planetary scales. Earth is about 8,000 miles across. The moon sits roughly 240,000 miles away. That seems far, but it's nothing compared to our distance from the sun. 93 million miles separate us from our star. If you wanted to drive there at highway speeds, it would take about 177 years of continuous driving. Mars, our neighboring planet, ranges from 34 million miles away at its closest to over 200 million miles at its farthest. Jupiter orbits at an average distance of 480 million miles from the Sun. Our solar system is essentially a few tiny rocks and gas balls scattered through a colossal volume of nothingness. If you think of the solar system as having things in it, you're wrong. It's more accurate to say it has a few dust specks in a warehouse. Now, let's talk about the gaps between stars. Proxima Centauri, our sun's nearest neighbor, sits about 25 trillion miles away. Get in a car and drive toward it at 60 miles per hour, and you'll arrive in roughly 47 million years. Take our fastest spacecraft ever built, the Parker Solar Probe, which can reach speeds of 430,000 miles per hour, and you'd still need about 6,000 years to get there. Our galaxy, the Milky Way, stretches about 100,000 light years across. 1 light year equals roughly 6 trillion miles. So we're talking about 600,000 trillion miles from one side of the galaxy to the other. And this enormous volume contains somewhere between 100 billion and 400 billion stars. The Andromeda Galaxy, our nearest large neighbor, sits about 2.5 million light-years distant. That's roughly 15 quintillion miles. And what's between us and Andromeda? A few dwarf galaxies. Some diffuse gas clouds, but mostly just vacuum. The observable universe measures about 93 billion light-years across, 550 septillion miles. And if you took all the matter in this observable cosmos and spread it evenly throughout the volume, you'd have approximately 1 hydrogen atom per cubic meter, 1 single atom in a space the size of a large refrigerator. We live in a cosmos that is overwhelmingly, staggeringly barren. Now we get to the really strange part. The vacuum isn't actually vacant. Let me explain. In 1927, a physicist named Werner Heisenberg formulated something called the uncertainty principle. The basic idea, stripped of complex mathematics, is that at quantum scales you can never know everything about a particle simultaneously. The more precisely you measure one property, the less precisely you can know another. This principle has a bizarre consequence for what we call nothingness. If a region of space were truly, completely devoid of content, we would know everything about it. We'd know exactly where all the particles are, because there wouldn't be any. We'd know exactly how fast they're moving, because they wouldn't be moving at all. But Heisenberg's uncertainty principle forbids this level of certainty. So what happens? Reality itself starts to fluctuate. Particle pairs pop into existence from nowhere, exist for infinitesimally brief moments, then annihilate each other and vanish. These are called virtual particles, and they're appearing and disappearing everywhere, constantly. Right now, as you're reading this, trillions upon trillions of these virtual particles are materializing and dematerializing in the region around you, inside you. In the gaps between the atoms that compose your body. This isn't just theoretical speculation. We've measured the effects directly. There's an experiment called the Casimir effect. Take 2 uncharged metal plates and position them extremely close together in a vacuum. The plates will be pushed together by a measurable force. What's creating this force? The virtual particles. There are more of them popping into existence outside the plates than in the narrow gap between them, creating a pressure differential. In 1997, physicists finally achieved precise measurements of this effect. They positioned two plates about 1/10,000th of an inch apart and measured an attractive force of roughly 1/100th of a pound per square inch. So the vacuum seethes with activity. It's a boiling quantum foam of particles constantly appearing and disappearing. The vacuum has energy, it's doing things, it's influencing reality. These virtual particles exist for such brief time periods that they exploit a loophole in physics. Energy and time have an uncertainty relationship. For extremely brief time periods, energy conservation can be violated. The shorter the time period, the larger the allowed energy violation. Virtual particles borrow energy from nothing, but repay it so quickly that the universe's bookkeeping doesn't notice. This means the vacuum is constantly fluctuating in energy. At any given moment, the vacuum's energy might be higher or lower than average. On average, it balances out. But at any specific point in space and time, energy is constantly shifting randomly. Reality at the quantum level isn't solid and deterministic. It's probabilistic and uncertain, constantly churning. The vacuum is less like smooth fabric and more like boiling foam. At scales smaller than roughly 10 to the negative 35 meters, the Planck length, space, and time themselves break down into chaotic fluctuations. This is quantum foam. Space isn't smooth and continuous at these scales. It's turbulent and uncertain. These quantum fluctuations aren't just theoretical curiosities. They have measurable effects beyond the Casimir force. They affect how light propagates through vacuum. They influence atomic energy levels in measurable ways. They contribute to the slight difference between electromagnetic moment and theoretical predictions. The vacuum is actively participating in every physical process, and these fluctuations might be the reason anything exists at all. In the earliest moments following the Big Bang, when the entire universe was smaller than an atom, quantum fluctuations in the fabric of reality itself might have created tiny variations in density. These minute irregularities eventually grew into galaxies, stars, and planets. Without those quantum fluctuations in the vacuum, the universe might have remained perfectly smooth and uniform. No structure would have formed. No stars, no planets, no life. The vacuum, with its inherent quantum uncertainty, might be the reason you exist. If you think the regions between stars seem barren, you haven't encountered cosmic voids yet. These are areas that make the rest of space look positively crowded by comparison. The universe isn't uniform in its distribution of matter. Instead, galaxies arrange themselves along filaments, like beads on cosmic strings, forming what astronomers call the cosmic web. These filaments surround enormous, hollow regions. These hollow areas are the cosmic voids. A typical cosmic void spans about 150 million light-years. That's approximately 900 quintillion miles of almost pure vacuum. There might be a handful of small galaxies scattered within such a volume, but they're incredibly rare. If you could somehow position yourself in the center of a cosmic void and look around, you might not see a single galaxy in any direction. Just darkness. Unbroken darkness stretching for millions of light-years. The Boötes void, discovered in 1981, ranks among the largest structures we've identified. It measures roughly 330 million light-years in diameter. In a region that size, you'd normally expect to find approximately 2,000 galaxies based on average cosmic density. The Boötes void contains about 60. Imagine belonging to a civilization on a planet in one of those 60 isolated galaxies. When you looked up at your night sky, you'd see almost nothing. Perhaps a handful of neighboring galaxies, if you were fortunate. But mostly just blackness. You'd have no way of knowing that the broader universe teems with hundreds of billions of galaxies, because you'd be trapped in this enormous bubble of nothingness. The edges of these voids aren't sharp boundaries. They're gradual transitions from nearly barren space to the cosmic web filaments where galaxies cluster. These transition zones are fascinating because they represent regions where the universe is actively becoming more void-like as expansion continues. Galaxies at void edges are being stretched apart. Some fall toward the denser filaments, pulled by gravity. Others drift deeper into the void, pushed by expanding space. What's particularly troubling is what this means for any civilizations in edge galaxies. They're in a transitional zone. Their descendants, billions of years from now, will either live in a galaxy that's merged into a larger cluster, surrounded by other galaxies, or they'll find themselves increasingly isolated as their galaxy drifts into the void. For those drifting into voids, the future is bleak. They'll watch over eons as neighboring galaxies slowly disappear. The night sky will gradually grow darker. Eventually, they'll be alone in a boundless bubble of darkness. This is happening right now. The voids are growing. As dark energy pushes the universe apart, voids expand while filaments of galaxies grow thinner and more isolated. Eventually, all of space might become one gigantic void with tiny, widely separated clusters of galaxies scattered throughout incomprehensible distances. Let's talk about what the vacuum does to matter and living tissue. Because it's not just barren, it's actively hostile to life. First, consider temperature. In space, there's virtually nothing to conduct heat away from your body. The background temperature hovers around -454 degrees Fahrenheit, only a few degrees above absolute zero. But temperature behaves counterintuitively in vacuum. If you were exposed to sunlight in near-Earth orbit, you'd face a bizarre situation. The side of your body facing the sun would heat dramatically, potentially reaching temperatures over 200 degrees Fahrenheit. The shadowed side would radiate heat into the vacuum, cooling toward the background temperature. You'd be simultaneously roasting and freezing. This extreme temperature differential would be agonizing. Parts of your body separated by mere inches would experience temperature differences of hundreds of degrees. Farther from any star, in deep interstellar regions, you'd simply radiate heat steadily. With no atmosphere to conduct heat away, you'd cool relatively slowly, perhaps taking hours rather than minutes to freeze solid. At the background temperature, molecular motion nearly stops. Chemical reactions cease. If any cells somehow survived freezing, they'd enter near complete stasis. No metabolism, no decay. Just frozen structure drifting through the cold. Then there's the pressure problem. On Earth's surface, atmospheric pressure is about 14.7 pounds per square inch. In vacuum, that pressure drops to essentially zero. This creates a differential. Your body contains internal pressure from blood vessels, lungs, digestive system. On Earth, external atmospheric pressure balances this. In vacuum, there's no external pressure to counterbalance. If you were suddenly exposed, you wouldn't explode like in movies, but you'd have roughly 15 seconds before losing consciousness. The lack of external pressure would cause liquids in your body to vaporize. Your blood wouldn't exactly boil because it's contained within blood vessels, but moisture on your tongue, in your eyes, and throughout your lungs would begin to boil away. You'd swell as dissolved gases in your bodily fluids came out of solution. Water's boiling point depends on pressure. At sea level, water boils at 212 degrees Fahrenheit. Reduce the pressure enough, and water boils at body temperature. In the near zero pressure of vacuum, it boils at even lower temperatures. If you held your breath during sudden decompression, the expanding air in your lungs would cause severe damage, potentially rupturing lung tissue. This is why the first rule of emergency decompression is exhale immediately. Dissolved gases in your bloodstream would come out of solution, forming bubbles. This is decompression sickness, similar to what scuba divers experience surfacing too quickly, except far more severe and happening far more rapidly. These bubbles could block capillaries, preventing oxygen delivery to tissues, causing organ damage. After approximately 90 seconds, you'd be dead. Not from explosion or blood boiling, but from oxygen deprivation and cumulative decompression damage. Your skin is tougher than you might think. It wouldn't rupture. You'd swell. You'd be in extreme distress, but you wouldn't burst apart. And if your body were left floating in space, it would never decompose normally. There are no bacteria in vacuum, no oxygen for oxidation. Your corpse would eventually break down through radiation damage and impacts from micrometeorites, but this would take extraordinarily long. You'd essentially mummify, freeze, dried by the vacuum. Over millions and billions of years, cosmic radiation would systematically tear apart the molecules composing your body. High-energy particles called cosmic rays would gradually disintegrate your structure. Eventually, you'd be reduced to individual atoms, each drifting separately through the nothingness. And those atoms would probably never reassemble or even encounter other matter again. Space is so sparse that once your atoms dispersed, the probability of them ever interacting with anything else approaches zero. They drift alone through the expanding universe for eternity. The vacuum wants to equalize you with itself. It wants to eliminate pressure differentials. It wants to make you as barren as the surrounding space. But quantum fluctuations are just the beginning. The vacuum appears to have its own intrinsic energy, separate from quantum effects. We call this dark energy, and it represents one of physics' greatest mysteries. Here's how we discovered it. In the 1920s, astronomer Edwin Hubble made a startling observation. The universe is expanding. Galaxies are receding from each other. For decades, astronomers assumed this expansion must be slowing down. Gravity pulls everything together, after all. The expansion should decelerate over time. In 1998, two independent research teams decided to test this assumption. They studied distant supernovas using these stellar explosions as standard candles to measure cosmic distances. What they found shocked the scientific community. The expansion isn't slowing down, it's speeding up. Both teams spent months checking and rechecking their data, convinced they'd made an error. They hadn't. The universe's expansion is accelerating. Something is pushing space apart, and that something seems to be space itself. We call this mysterious phenomenon dark energy, and it constitutes approximately 68% of the total energy in the universe. It's everywhere, in the regions between galaxies, between stars, between planets, in the room where you're sitting right now. And it's relentlessly pushing everything apart. Think about the implications. The vacuum has a kind of anti-gravity built into its very nature. The more vacuum you have, the more dark energy you have, and the harder it pushes outward. As the universe expands, more vacuum is created, which means more dark energy, which means faster expansion, which creates even more vacuum. It's a runaway process with no brakes. The quantum vacuum doesn't just have zero pressure. In a sense, it has negative pressure. This is related to dark energy. Normal matter and energy have positive pressure. When you compress them, they push back. But dark energy behaves oppositely. It has negative pressure, which means it pulls inward on itself while pushing outward on its surroundings. This creates a repulsive gravitational effect, causing accelerating expansion. The nothingness is fighting against itself. The vacuum's own properties cause it to expand, creating more of itself, which causes more expansion. It's self-replicating nothingness, growing exponentially over cosmic timescales. The vacuum isn't passive. It's aggressively expanding, consuming everything, turning matter and energy into ever more thinly distributed nothingness over time. We've talked about the vacuum and dark energy extensively, but there's another mystery permeating seemingly barren space: dark matter. Dark matter doesn't emit, absorb, or interact with light. The only way we know it exists is through gravity. Galaxies rotate too fast. Galaxy clusters hold together too tightly. Light bends more than it should. Something with mass is out there, pulling on things gravitationally, completely invisible. Dark matter makes up about 27% of the universe. That's 5 times more than ordinary matter. Everything you can see makes up less than 5%. Most matter is invisible, and it's around us right now. Dark matter fills our galaxy. Trillions of dark matter particles stream through you every second, and you can't feel them because they barely interact with regular matter. We don't know what dark matter is made of. The leading theory suggests exotic particles that interact only through gravity. We've built enormous detectors deep underground, trying to catch these elusive particles. So far, we have no definitive detection. So the vacuum isn't just filled with dark energy. It's also permeated with dark matter. The nothingness is crowded with invisible phenomena. Let me tell you about neutrinos, another class of particles filling supposedly barren space. Neutrinos are tiny particles with almost no mass. They barely interact with anything. Right now, approximately 400 trillion neutrinos are passing through your entire body every second. Most originate from the sun, produced through nuclear fusion reactions. A neutrino could pass through a light year of solid lead and have a 50-50 chance of not interacting with a single atom. To a neutrino, Earth might as well not exist. Solid rock is transparent. The cosmic neutrino background fills all of space with neutrinos left over from the Big Bang. Approximately 336 neutrinos per cubic centimeter exist everywhere in the universe. The vacuum is full of these ghost particles, streaming through everything, interacting with almost nothing. There's more. Galaxies possess magnetic fields. The regions between stars contain them. Even intergalactic space has faint magnetic fields permeating it. These fields are incredibly weak, millions or billions of times weaker than Earth's magnetic field. But they exist, threading through the vacuum, organizing how matter and energy behave. Interstellar space contains tiny dust grains, mostly carbon and silicates, floating between stars. These grains are microscopic, typically less than 1 micrometer across. But sufficient quantities exist to block our view of the galactic center. These specks are remnants of dead stars, material processed through stellar fusion, expelled in supernova explosions, now spreading through space. They provide surfaces where molecules can form. The vacuum is filled with high-energy cosmic rays, mostly protons racing through space at nearly light speed. They originate from supernova explosions, pulsars, active galactic nuclei. The most energetic carry energies, around 10 to the 20th electron volts. That's roughly the energy of a baseball thrown at 50 miles per hour, except concentrated in a single subatomic particle. You're being struck by muons, particles created when cosmic rays hit our atmosphere at about 1 per square centimeter per minute. The nothingness is dangerous. It's filled with high-energy particles that can damage DNA and cause cancer. This represents one of the biggest challenges for long-term space travel. Even the regions between stars aren't truly vacant. Astronomers call this the interstellar medium. It contains approximately 1 atom per cubic centimeter on average. It's organized into different phases with varying temperatures and densities. Hot ionized medium, heated to millions of degrees. Warm neutral medium at roughly 15,000 degrees. Cold neutral medium, around 100 degrees. And molecular clouds, the coldest and densest regions where stars form. But even the densest molecular clouds are incredibly sparse by terrestrial standards. They might contain 10,000 to 1,000,000 particles per cubic centimeter. For comparison, the air you're breathing contains approximately 10 to the 19th particles per cubic centimeter. Even the densest interstellar regions are roughly 1 trillion times less dense than air. So the vacuum isn't just filled with dark energy and dark matter. It's permeated with neutrinos, magnetic fields, dust, cosmic rays, and diffuse gas. The nothingness is crowded with invisible phenomena. Let's talk about loneliness. Real, absolute isolation. The kind that comes from being surrounded by nothingness on a cosmic scale. The Voyager 1 spacecraft launched in 1977. After visiting Jupiter and Saturn, it kept going, heading into the emptiness beyond our solar system. In August 2012, Voyager 1 crossed the heliopause, where solar wind gives way to the interstellar medium. It became the first human-made object to enter interstellar space. Voyager 1 is now approximately 15.8 billion miles from Earth. At that distance, a radio signal traveling at light speed takes about 23 hours to reach it. If you could somehow stand on Voyager and look back, the sun would appear as just another star, brighter than its neighbors but not dramatically so. Earth would be invisible, lost in the glare. The spacecraft travels at roughly 38,000 miles per hour relative to the sun, fast by human standards. But it would still require about 40,000 years to reach the nearest star if it were headed in that direction, which it isn't. What's it like out there? Voyager's instruments provide data. Plasma density is higher than within the heliosphere, but still incredibly low. The magnetic field differs, more cosmic radiation, but mostly it's just barren. Regions between stars, with merely a few atoms per cubic centimeter, and the spacecraft itself. Voyager will drift through interstellar space for millions of years. Its power source will die sometime in the late 2020s. Afterward, the spacecraft will be silent, dark, coasting through nothingness on momentum alone. No course corrections, no maneuvers, just drifting. It will pass through regions where nothing interesting happens for thousands of years at a time. We built this spacecraft. We attached a golden record containing sounds and images from Earth, a message for any alien civilization that might discover it. The reality? Nobody probably ever will. Voyager 1 is going to drift through the emptiness between stars alone, for longer than our civilization has existed, longer than our species has existed, possibly longer than Earth itself will exist. Eventually, perhaps in billions of years, Voyager might pass near enough to a star to be affected by its gravity, maybe captured into orbit, maybe just passing by. Either way, by that time, Earth will be gone, consumed when our sun becomes a red giant. Voyager will be the sole remaining evidence that we ever existed. a tiny assemblage of metal, plastic, and plutonium, drifting through nothingness, carrying sounds and images from a planet that no longer exists. That's the kind of isolation the vacuum creates. Absolute, total, permanent separation. Now, scale this up cosmically. We've transmitted radio signals into space, some deliberately, like the Arecibo message sent in 1974, most accidentally, as our broadcasts leak into space. These signals travel at light speed, forming an expanding bubble around Earth, now about 100 light years in radius. Within that bubble, there are perhaps a few hundred stars. Some might have planets. Maybe one harbors life intelligent enough to detect our transmissions. But that bubble is expanding into a galaxy 100,000 light-years across. And our galaxy is just one among trillions. The chances that anyone will ever detect our signals are vanishingly small. And even if someone did hear us, the distances create both spatial and temporal isolation. Factor in civilizations rising and falling across billions of years, separated by thousands of light years, with technological windows that might only last thousands of years. The combination makes contact mathematically improbable, regardless of how many civilizations exist. The vacuum doesn't just separate us spatially, it separates us temporally. The combination makes connection impossible. We might be surrounded by civilizations in the cosmic sense, but isolated from all of them by an uncrossable barrier of distance and time. Here's another strange property. The vacuum has a built-in speed limit. The speed of light in vacuum is exactly 299,792,458 meters per second. Why that specific number? We have no idea. It simply is. This speed limit has profound implications. You can never know what's happening right now anywhere else in the universe. When you look at the sun, you're seeing it as it was 8 minutes ago. The nearest star? You're seeing it as it was 4 years ago. Light speed creates a horizon around you. Information from beyond a certain distance hasn't had time to reach you yet. And if the universe is expanding faster than light speed beyond a certain point, information from beyond that point will never reach you. The vacuum limits how much of reality you can ever interact with or even know about. It separates things not just spatially, but causally. But time itself behaves differently in vacuum depending on conditions. Einstein's relativity tells us that time and space are connected. They form a four-dimensional fabric called spacetime, and this fabric can be warped. When you warp space, you also warp time. In regions of intense gravity, time slows down relative to regions of weaker gravity. This isn't science fiction, it's measurable. GPS satellites orbit about 12,000 miles above Earth, where gravity is slightly weaker. Time passes slightly faster for them than for us on the surface, about 38 microseconds per day faster. GPS systems must correct for this, or navigation would drift by miles each day. In deep intergalactic regions, far from stars and galaxies, time runs at its maximum rate. This is as fast as time can flow in our universe. If you could somehow exist in perfect isolation in intergalactic vacuum, time for you would pass normally from your perspective. But relative to observers near massive objects like Earth, your time would be flowing faster. You'd age more quickly than people on planets. The vacuum doesn't just separate us in space. It creates temporal islands where time itself flows at different rates. We're all traveling through time at different speeds, depending on where we are in the cosmos. Let's examine what happens when you warp the vacuum to its extreme. Black holes. A black hole forms when you compress enough mass into a sufficiently small region that the warping of spacetime becomes so severe not even light can escape. At a black hole's center, according to current understanding, lies a singularity, a point of infinite density where our physics breaks down completely. But here's the strange part. Most of a black hole is vacuum. The singularity might be infinitely small. The event horizon, the point of no return, can span many miles for a stellar mass black hole or millions of miles for a supermassive black hole. Between the event horizon and the singularity, vacuum. Extremely warped vacuum, falling inward at light speed, but still fundamentally vacuum. If you fell into a large black hole, you might not even notice crossing the event horizon initially. Space would appear mostly normal around you. You'd simply be falling, accelerating, surrounded by nothingness. The vacuum inside a black hole is probably the most extreme form of nothingness in the universe. Its vacuum so warped that it's falling into itself faster than light can travel outward. And black holes don't last forever. Through Hawking radiation, discovered by Stephen Hawking in 1974, black holes slowly emit particles and lose mass. Eventually, a black hole evaporates completely. What remains? Vacuum. The most extreme warping of space imaginable, the densest concentration of matter possible, eventually returns to just vacuum. Even black holes are temporary. In the end, there's only nothingness. Einstein's general relativity describes gravity not as a force pulling objects together, but as the curvature of space-time. Mass and energy warp space around them, and objects move along curves in that warped fabric. So vacuum can be curved. Space without matter can still possess geometry, can bend and twist. A gravitational wave is literally a ripple in the curvature of vacuum. Space itself oscillating, stretching and squeezing as the wave propagates. We've detected these ripples. In 2015, LIGO, the Laser Interferometer Gravitational Wave Observatory, detected distortions caused by two black holes colliding over 1 billion light-years away. The wave stretched and squeezed space by an amount smaller than a proton's width. But it was measurable. What does this tell us? The vacuum is real. It's not merely the absence of stuff. It's an entity that can ripple and wave. It has properties. It can be measured. But if vacuum can curve and ripple, what is it made of? What's actually bending? We don't know. We can describe it mathematically. We can measure effects. But we don't understand what it fundamentally is. Let's examine the regions between galaxies more closely, because they represent the most desolate locations in the known universe. Interstellar space, the regions between stars within a galaxy, averages about 1 atom per cubic centimeter. That's sparse. But intergalactic space is far more barren. The regions between galaxies contain roughly 1 atom per cubic meter, 1,000 times less dense. Imagine somehow finding yourself in deep intergalactic space, millions of light years from the nearest galaxy. What would you observe? With the naked eye, probably nothing. The nearest galaxies would be so distant they'd appear as faint smudges, if visible at all. No individual stars would be discernible. You're too far from any galaxy to resolve stellar objects. Just darkness, profound darkness, in every direction. The temperature would hover just above absolute zero. No stellar radiation would warm you except the cosmic microwave background at -454 degrees Fahrenheit. You'd exist in the most barren, darkest, coldest location imaginable, surrounded by nothingness for millions of light years in every direction. and you'd remain there indefinitely because there's nothing to push against, no way to alter your trajectory. You drift through that desolation effectively forever, or until eventually, after tens of millions of years, approaching close enough to a galaxy for its gravity to capture you. This represents the universe's default condition. Not stars and planets and life, vacuum. Cold, dark, silent. Everything else, all the matter and energy and activity, constitutes rare exceptions. Here's another eerie aspect. The vacuum is absolutely silent. Sound is vibration traveling through matter, through air or water or solids. In the vacuum, there's insufficient matter to transmit sound waves. If you were in space and a star exploded a mile away, you'd see the blinding light. You might feel the radiation, but you'd hear nothing. Perfect silence. This is one aspect films get fundamentally wrong. All those explosions and whooshes and laser sounds in space, none of that would happen. Space battles would occur in complete silence. Ships would be destroyed soundlessly. The most violent events in the universe, supernovas releasing more energy in seconds than the sun will emit in its entire lifetime, happen in perfect silence. The vacuum doesn't just separate things physically, it creates acoustic isolation. Even if you were somehow near someone in space, close enough to see them, their screams wouldn't reach you. You could watch them die in silent slow motion, unable to hear their last words. This silence is absolute. On Earth, even in the quietest places, there's always some sound. Air moving, your heartbeat, blood flowing through your ears. In the vacuum, there's nothing. No background hum, no subtle vibrations. Just silence so complete, it's difficult to imagine if you've never experienced it. This acoustic isolation adds another layer to the vacuum's hostility. It cuts off one of the primary ways we interact with our environment and communicate with each other. In the vacuum, you could be surrounded by activity and remain in perfect silence, disconnected from it all. Let's return to the atomic scale and consider something deeply troubling. The vacuum inside matter isn't quite the same as the vacuum outside matter. We said atoms are mostly emptiness, but the vacuum inside an atom is influenced by the electromagnetic fields of the nucleus and electrons. These fields permeate the gaps, changing the properties of the vacuum itself. In a sense, there are different kinds of vacuum. The vacuum inside a proton is different from the vacuum inside an atom, which is different from interstellar vacuum, which is different from intergalactic vacuum. They're all mostly nothingness, but the subtle differences in quantum field configurations make them distinct. This raises a philosophical question. If the vacuum can have different properties in different locations, is it really vacuum? Or is it more accurate to say that true vacuum doesn't exist anywhere in our universe? That everywhere, the nothingness is subtly different, shaped by nearby matter and energy? Perhaps complete and total nothingness is impossible in our cosmos. Perhaps the very act of asking, what would truly empty space be like, is meaningless, because our universe doesn't contain any truly empty space. Every region is influenced by quantum fields, by distant matter, by the cosmic microwave background, by dark energy. The vacuum might be fundamentally relative, not absolute. There might be no such thing as pure nothingness, only varying degrees of near nothingness, each slightly different from the others. If true, this means the baseline state of our universe isn't nothing. It's something pretending to be nothing. A quantum foam of fields and fluctuations that appears empty but never truly is. Here's another strange quantum effect. The vacuum can screen electric charges. When you place an electric charge in vacuum, quantum fluctuations respond. Virtual electron-positron pairs pop into existence near the charge. The charge slightly attracts the virtual particles with opposite charge and repels those with same charge. This creates a cloud of virtual particles around the real charge, partially screening it. This means the effective charge you measure depends on how close you get. From far away, you measure less charge because of screening. Get closer, and you penetrate the screening cloud, measuring more charge. The vacuum is polarizing like a dielectric material, except it's doing it through quantum fluctuations rather than physical molecules. This vacuum polarization affects how forces work at different distances and energies. The vacuum isn't passive. It actively mediates interactions between particles, changing how forces behave based on distance and energy. Let's discuss the oldest light in the universe, traveling through vacuum for nearly 14 billion years. When the universe was approximately 390,000 years old, it was filled with hot plasma. Photons couldn't travel freely because they kept bouncing off electrons. Then the universe cooled enough for atoms to form, and photons could suddenly travel without obstruction. The cosmos became transparent. Those photons have been traveling ever since. We call this the cosmic microwave background, or CMB. It fills all of space. Right now, CMB photons are passing through your body. They've been traveling for 13.8 billion years. The CMB has been redshifted by cosmic expansion from visible light to microwaves. Its temperature is approximately -454 degrees Fahrenheit. The CMB displays tiny temperature fluctuations that were the seeds of everything that exists today. Those minute density variations eventually grew into galaxies, stars, and planets. But here's the ominous trajectory. As the universe continues expanding, the CMB will redshift further. Eventually, it will be stretched so much it becomes undetectable. Future civilizations, trillions of years from now, won't be able to observe it. They'll have no evidence of the Big Bang. The expansion is erasing cosmic history, hiding the evidence of our origins by pushing it beyond our ability to detect. Let's discuss the future. It's grim. As the universe expands and dark energy continues pushing galaxies apart, the future grows lonelier and more barren. In approximately 4 billion years, the Milky Way and Andromeda will collide and merge, forming what astronomers call Milkomeda. But that represents one of the last major cosmic events. Afterward, the universe enters a long, slow decline. Star formation will slow as galaxies exhaust their hydrogen gas. The last stars will form roughly 100 trillion years from now. After that, no new stars. The universe gradually grows darker as existing stars burn out. In approximately 10 to the 14th years, 100 trillion years, the last conventional stars will die. Afterward, only light from slowly cooling white dwarfs, neutron stars, and evaporating black holes will remain. By 10 to the 37th years, most stars will have either been ejected from galaxies or fallen into central black holes. Galaxies as we know them won't exist. Just isolated stellar remnants drifting through ever-expanding vacuum. By 10 to the 40th years, even stable matter might decay. Protons could break down into lighter particles. If this happens, even planets and dead stars will eventually dissolve into radiation. By 10 to the 100th years, black holes will have evaporated through Hawking radiation. The last supermassive black holes at galaxy centers will take longest, but eventually, even they vanish. What remains? Vacuum. Photons stretch to wavelengths longer than the observable universe by expansion, individual electrons and positrons separated by distances exceeding the current size of the observable universe. And dark energy, pushing space apart faster and faster. This is the heat death, the big freeze. The universe reaches maximum entropy. No energy gradients remain to perform work. No structure, no change. Just vacuum, expanding forever, growing more barren, colder, darker for eternity. Entropy measures disorder. The second law of thermodynamics states that entropy always increases in closed systems. The universe is a closed system. There's nothing outside it adding order or removing entropy. So cosmic entropy must always increase. As entropy increases, structures break down, stars burn out, galaxies disperse, matter decays. Eventually, everything becomes uniformly distributed, low-energy radiation spreading through expanding space. The final state is maximum entropy, perfect uniformity, perfect isolation, perfect stillness. This is our cosmos's fate. Not a dramatic end, a slow fade into nothingness. Here's one of physics' greatest embarrassments. When we try to calculate how much energy the vacuum should have based on quantum mechanics, we get an answer that's catastrophically wrong. Quantum field theory predicts that even in its lowest energy state, the vacuum should be seething with zero-point energy. Virtual particles popping in and out of existence should contribute enormous energy density. How much energy? When physicists calculate it, they get a number approximately 10 to the 120th times larger than what we actually observe. That's not a small error. That's the worst prediction in the history of physics. We're off by a factor of 1, followed by 120 zeros. Either our calculations are fundamentally wrong in ways we don't understand, or there's some mechanism cancelling out almost all of the vacuum energy, leaving only the tiny residual we observe as dark energy. Nobody knows which. Nobody knows how to fix the calculation. We're confident the universe is expanding, accelerating, heading toward heat death. But that confidence rests on measurements of something we fundamentally don't comprehend. The vacuum is mysterious, not just in what it does, but in what it is. Here's a truly strange thought. Could consciousness itself be related to the structure of vacuum? Your thoughts, your sense of self, your awareness, all arise from electrochemical processes in your brain. Those processes depend on electrons moving between atoms. Those electrons are excitations in quantum fields permeating the vacuum. The forces guiding those electrons are carried by virtual photons popping in and out of the vacuum. At a fundamental level, your consciousness might be patterns in the quantum vacuum. Not just sitting in the vacuum, but made of vacuum processes. Your awareness might be vacuum becoming aware of itself in a very literal sense. This is speculative, bordering on philosophical rather than scientific. But if we're made mostly of structured nothingness, and our consciousness arises from quantum processes in that structure, then perhaps consciousness is a property that emerges when nothingness organizes itself in sufficiently complex patterns. Every thought you've ever had involved quantum processes happening in the vacuum of your brain. The vacuum isn't just the stage where your neurons fire. It's an active participant in the process. Virtual particles mediate the forces that let your neurons communicate. Quantum fields carry the signals. At a fundamental level, thinking is vacuum doing something. Consciousness might be what it feels like when vacuum organizes itself into sufficiently complex patterns. You might literally be nothingness that learned to think, and every thought you have might be the vacuum examining itself. Here's a troubling thought experiment. The vacuum might be exactly as it is because if it were different, we wouldn't exist to observe it. The fundamental constants of physics, including properties related to vacuum and dark energy, appear finely tuned for the existence of complexity and life. Change them even slightly, and the universe becomes hostile to structure formation. If dark energy were slightly stronger, it would have prevented galaxies from forming. Matter would never have clumped together into stars and planets. No life could arise. If it were weaker, the universe might have recollapsed in a big crunch before life could evolve. If vacuum properties were different, atoms might not be stable. Stars might not function. Chemistry as we know it might not exist. This is the anthropic principle. The universe appears fine-tuned for our existence because we can only observe a universe capable of producing observers. But this raises questions. Why these specific values? Why this universe? One explanation is the multiverse hypothesis. Perhaps countless universes exist with different fundamental constants. Most are sterile, incapable of producing complexity or life. We find ourselves in one of the rare universes where the constants permit our existence, not because the universe was designed for us, but because we can only exist in a universe with these properties. If true, this means the vacuum we observe, with all its strange properties and apparent fine-tuning, is just one possibility among infinite variations. Most universes are even more hostile to life than ours. We happen to exist in one of the rare exceptions. The vacuum that terrifies us might be one of the friendliest possible vacuums. In most other universes, things are worse. Dark energy creates another alarming problem, an information horizon. As expansion accelerates, there's a sphere around us, beyond which information can never reach us, no matter how long we wait. This isn't because the information travels slowly. It's because space is expanding too rapidly for the information to ever cover the distance. This horizon is currently about 14 billion light-years away, but it's shrinking in terms of what we can newly observe. Objects currently just inside the horizon will eventually cross it and become permanently inaccessible. What's disturbing is what this means for future civilizations. A civilization arising trillions of years from now in our galaxy will look outward and see almost nothing. The cosmic microwave background will have redshifted into undetectability. Distant galaxies will have receded beyond the horizon. They'll have no evidence of the Big Bang, no way to deduce that the universe had a beginning or is expanding. Their cosmology will be fundamentally limited by the information horizon. They might conclude their galaxy is the entire universe, surrounded by infinite, static darkness. They'd be wrong, but they'd have no way to know they're wrong. The vacuum, through its expansion, is erasing the history and structure of the universe. Future observers will be cut off from knowledge that we currently possess, not because they're less intelligent, but because the evidence will have expanded beyond their light cone. We live in a special epoch, an epoch where we can still observe the full richness of the cosmos. Future epochs won't be so fortunate. Let's discuss the edge of the observable universe, where the vacuum becomes truly incomprehensible. The observable universe measures approximately 93 billion light-years across. That's the distance light has traveled since the Big Bang, accounting for cosmic expansion. Everything beyond that lies outside our cosmic horizon. We cannot see it, detect it, or interact with it in any way. But what exists beyond the observable universe's edge? More vacuum, more galaxies, more stars. As far as we can determine, reality might be infinite. Or it might curve back on itself in higher dimensional ways we can't directly observe. We don't know. If the universe is infinite, the implications are staggering. An infinite universe contains infinite matter and infinite vacuum, infinite galaxies, infinite stars, infinite planets. In an infinite universe, every possible arrangement of matter exists somewhere. There would be infinite planets, exactly like Earth, infinite versions of you. But here's the catch. Even in an infinite universe, you'd still be isolated by vacuum. Your nearest duplicate might be 10 to the 100th light years away, a distance so vast that even in the trillions of years before heat death, light from them could never reach you. The vacuum creates islands of causality, regions that can interact, surrounded by regions they can never contact. Even in an infinite universe filled with infinite matter, the regions separating things are so immense that most of reality might as well not exist from your perspective. Here's something that seems paradoxical. The vacuum has weight, or more precisely, it has energy, and according to Einstein's equation, E equals mc squared, energy and mass are equivalent. Dark energy pervades the vacuum with an energy density that has a mass equivalent. If you add up all the dark energy in the observable universe and convert it to mass, you get approximately 10 to the 54th kilograms. For comparison, all ordinary matter in the observable universe totals roughly 10 to the 53rd kilograms. The vacuum's energy content outweighs everything in it by a factor of 10. The nothingness has more mass equivalent than all the stars, planets, gas clouds, and galaxies combined. This means the universe is dominated by the properties of its vacuum. The future of reality is determined by what the vacuum does. We're not the main characters in the cosmic story. The vacuum is. We're a minor subplot, brief interruption in the story of nothingness. Here's another troubling aspect. The mere act of observing the vacuum changes it. This is a consequence of quantum mechanics. At quantum scales, measurement isn't passive observation. It's active interaction that affects what you're measuring. The famous double-slit experiment demonstrates this. Electrons behave like waves when unobserved, like particles when measured. The act of measurement collapses the wave function. The vacuum is similar. When you try to measure vacuum properties at quantum scales, your measurement apparatus interacts with the quantum fluctuations, changing them. You can't observe the vacuum without disturbing it. This creates a fundamental limit on what we can know about the vacuum. We can never observe it in its truly undisturbed state, because observation requires interaction, and interaction disturbs the state. It's like trying to measure the temperature of a cup of water with a thermometer that's much hotter or colder than the water. The thermometer changes what it's measuring. At quantum scales, all measurements have this problem. So, when we talk about what the vacuum really is, we're facing a fundamental epistemological barrier. The vacuum in its natural, unobserved state might be fundamentally different from the vacuum we can actually measure. Reality might be literally unknowable at the deepest levels. Let's connect vacuum to particle physics, because the vacuum is actually where particle physics happens. When physicists talk about particles, they're really talking about excitations in quantum fields. Electrons are excitations in the electron field. Photons are excitations in the electromagnetic field. The fundamental reality isn't particles, it's fields permeating all of space. The vacuum is these fields in their lowest energy state. Particles are disturbances in the vacuum, ripples in the underlying fields. When particles collide in accelerators like the Large Hadron Collider, they're disturbing the vacuum with enormous energy, creating new excitations, new particles that quickly decay back to the vacuum state. The Higgs boson, discovered in 2012, is particularly interesting. The Higgs field permeates all of vacuum and gives mass to other particles through their interaction with it. Mass itself is a property particles acquire by interacting with the vacuum. So the vacuum isn't just the stage where physics happens. It's an active participant. Particles get their properties from vacuum interactions. The vacuum determines what kinds of particles can exist and how they behave. If the vacuum were different, if the Higgs field had a different value, for instance, particles would have different masses. Chemistry would work differently. Stars might not be able to form. Life might be impossible. The vacuum's properties determine the structure of physics itself. Change the vacuum, and you change everything built on it. Here's a truly alarming theoretical possibility. Our vacuum might not be stable. Quantum field theory suggests that the vacuum might exist in different energy states. What we call vacuum, the lowest energy state of space, might not actually be the lowest possible state. It might be a false vacuum, a metastable state that could decay to a true lower energy vacuum. If this happened, it would be catastrophic. A bubble of true vacuum could form spontaneously somewhere in the universe and expand at light speed. Anything in its path would be destroyed and reconstituted with different physical laws. The fundamental constants of nature might change. Atoms might become unstable. All existing structure might disintegrate. This vacuum decay would spread at light speed so you wouldn't see it coming. One moment everything's normal, the next you're gone, converted into whatever strange form matter takes in the true vacuum state. Is this likely? Probably not. Our vacuum has persisted for nearly 14 billion years. If it were easily destabilized, it likely would have decayed already. But we can't rule it out entirely. It's possible, though unlikely, that the vacuum itself is temporary, not just expanding and growing more barren, but potentially unstable at a fundamental level. The stage on which reality performs might collapse without warning, ending not just life, but all structure and potentially changing the laws of physics themselves. The vacuum is unsettling not just because of what it is, but because of what it might become. Let's discuss the cosmological constant, Einstein's biggest blunder that turned out to be his greatest prediction. When Einstein developed general relativity, the equations allowed for a cosmological constant, an intrinsic energy of space itself. Einstein added this term to keep the universe static, matching observations of his time, which suggested the universe wasn't expanding. When Hubble discovered cosmic expansion, Einstein abandoned the cosmological constant, reportedly calling it his biggest blunder. If he'd trusted his equations, he could have predicted cosmic expansion before it was observed. But the cosmological constant came back. When we discovered dark energy, accelerating cosmic expansion, physicists realized that what we call dark energy behaves exactly like Einstein's cosmological constant. It's a property of space itself, constant in density, causing expansion to accelerate. Einstein was right after all. Space does have an intrinsic energy. The vacuum itself has the cosmological constant built into it, but the value is wrong. Quantum field theory predicts the cosmological constant should be enormous, vastly larger than observed. This discrepancy remains unexplained. The vacuum has energy. We can measure it, but we can't explain why it has the value it does. It's one of the deepest mysteries in physics. Let's connect two extremes: the incomprehensibly large scale of cosmic voids and the incomprehensibly small scale of quantum foam. At the largest scales, we have cosmic voids hundreds of millions of light years across, regions so vast and barren that they contain only a handful of galaxies in volumes where thousands should exist. These voids represent vacuum at its most extreme macroscopic manifestation. At the smallest scales, we have quantum foam at the Planck length, 10 to the negative 35 meters. At this scale, space and time themselves break down into chaotic fluctuations. The vacuum isn't smooth, it's turbulent and uncertain. What connects these extremes? They're both fundamentally about nothingness. The cosmic voids are large-scale absences of matter. The quantum foam is small-scale uncertainty about whether anything exists at any given moment. Both challenge our intuitions about reality. We expect space to be smooth and continuous at large scales, but cosmic voids show us it's lumpy and irregular. We expect vacuum to be simple and empty at small scales, but quantum mechanics shows us it's complex and active. The vacuum defies our expectations at both extremes. Too large to comprehend, yet mostly barren. Too small to observe, yet seething with activity. Reality is stranger than our everyday experience prepares us for. How do you measure nothing? How do you quantify the absence of something? This is actually a profound question in physics. We can measure matter by its mass, its charge, its temperature. But how do you measure vacuum? You measure it by its effects. The expansion rate of space tells us about dark energy. The deflection of light tells us about space-time curvature. The Casimir effect tells us about quantum fluctuations. Virtual particle contributions to atomic energy levels tell us about vacuum properties. We can't observe the vacuum directly. We can only infer its properties from how it affects things that aren't vacuum. It's like trying to measure wind by watching leaves move. You can't see the wind itself, only its effects. This creates an interesting epistemological situation. Our understanding of what constitutes most of the universe is indirect. We're measuring absence by its influence on presence. We're studying nothingness through its interaction with something, and this raises questions. How confident can we be in our measurements? How much might we be missing because we can only detect certain kinds of effects? Could the vacuum have properties that don't manifest in ways we can currently measure? The vacuum might be far stranger than even our strange theories suggest, and we might not know because we lack the tools or concepts to detect those properties. Here's a concern that keeps some physicists awake at night. The Higgs field might not be in its lowest energy state. Measurements of the Higgs boson mass and the top quark mass suggest we might be in a metastable vacuum. The Higgs field, which permeates all of space, might be sitting in a local minimum of its potential energy, not the global minimum. If true, quantum tunneling could eventually cause the field to transition to the lower state. This would be vacuum decay, catastrophic, and spreading at light speed. Current measurements suggest that if this is possible, it wouldn't happen for at least 10 to the 100 years, far longer than the current age of the universe. So there's no immediate danger, but it means the vacuum we exist in might be temporary in the very long term, not just expanding and growing more diffuse, but potentially unstable and subject to catastrophic transition. The stage on which reality plays out might not be as stable as we'd like to think. Let me tell you about something strange that happened with our early deep space probes. The Pioneer spacecraft, launched in the 1970s, experienced an unexpected deceleration as they traveled through the outer solar system. This became known as the Pioneer anomaly. The spacecraft was slowing down more than they should based on known forces. The deceleration was tiny, about 8 billionths of a meter per second squared. But it was there, measurable, unexplained. For years, scientists puzzled over this. Was there an unknown force acting in the vacuum of the outer solar system? Some new physics we didn't understand? Dark matter effects? A property of vacuum itself? Eventually, the anomaly was explained through mundane causes. Thermal radiation from the spacecraft's power sources was creating a tiny but measurable push against the direction of travel. Mystery solved through careful analysis and modeling. But here's what's interesting. For a time, we had a genuine mystery about how vacuum behaves in the outer solar system. We observed an effect we couldn't explain with known physics. It reminded us that the vacuum might still hold surprises, that our understanding, while extensive, might not be complete. Even today, there are anomalies in spacecraft trajectories and observations that we can't fully explain. Most will probably turn out to have conventional explanations like the Pioneer anomaly did. But some might reveal new physics, new properties of vacuum we haven't discovered yet. The vacuum of space isn't a solved problem. It's an ongoing investigation. And every time we send probes farther from Earth into regions of space we've never explored, we're testing our understanding against reality. Sometimes reality surprises us. Let's zoom into a different scale. Not the vacuum between stars, but the vacuum between particles in what we call matter. When atoms bond to form molecules, the electrons don't actually touch. They're prevented from occupying the same space by quantum mechanical principles. The distance between atoms in a molecule is maintained by a balance of forces with vacuum in between. In a crystal lattice, atoms are arranged in regular patterns, but between each atom and its neighbors, vacuum. The solid structure you perceive when you touch a piece of metal is actually atoms floating in vacuum, held in place by electromagnetic forces acting across that vacuum. Take water, H2O. Two hydrogen atoms bonded to one oxygen atom. The nuclei of those atoms are separated by vacuum. The electrons orbit through vacuum. The molecule itself is mostly vacuum held together by forces acting across that vacuum. Your DNA, the double helix structure, its atoms arranged in a specific pattern with vacuum between all of them. The information that makes you who you are is encoded in the arrangement of atoms separated by vacuum. Life itself is patterns of atoms with vacuum between them. The complexity of biology, the machinery of cells, the information storage of genetics, all of it is structure imposed on vacuum. Without vacuum, without the gaps between atoms, none of it would work. The distances matter. The gaps matter. Biology is the vacuum organizing itself into self-replicating patterns. You are vacuum arranged in a specific way, and when you die, that arrangement dissolves, and the atoms that composed you drift apart, separated once again by vacuum. Here's one of the strangest phenomena in physics: quantum entanglement. When two particles become entangled, measuring one instantly affects the other, regardless of the distance separating them. This happens faster than light. In fact, it appears to be instantaneous, violating our intuition that information can't travel faster than light. Einstein called this spooky action at a distance, and was deeply troubled by it. But experiments have confirmed it repeatedly. Entangled particles separated by miles, even potentially by light years, remain connected in ways we don't fully understand. What does this tell us about vacuum? If two entangled particles can influence each other instantaneously across vast distances, the vacuum between them isn't really separating them. At some level, they remain connected through the quantum fields permeating space. The vacuum isn't creating total separation. At the quantum level, particles that have interacted can remain correlated across any distance. The nothingness between them doesn't break that connection. This suggests that the vacuum is more interconnected than it appears. That separation is, in some sense, an illusion. That at the deepest level, the quantum fields permeating all of space connect everything to everything else. Your particles have interacted with other particles. Those particles have scattered across Earth, into space, throughout the solar system. Some of your particles might be quantum entangled with particles millions of miles away. The vacuum separates you from them spatially, but not quantum mechanically. You're connected to the rest of the universe through quantum fields in ways we barely understand. The vacuum creates separation, but also connection. It's not simple isolation. It's complex interconnection through fields we can't see or feel, but that physics tells us must be there. Let's go back to the very beginning. What was the vacuum like in the earliest moments of the universe? In the first fraction of a second after the Big Bang, the universe was unimaginably hot and dense. Temperatures were so high that even atomic nuclei couldn't exist. The universe was a soup of fundamental particles and energy. But even then, there was vacuum. Or more precisely, there was spacetime with quantum fields permeating it. The vacuum state was radically different from today because of the extreme conditions, but it was still fundamentally vacuum. As the universe expanded and cooled, the properties of vacuum changed. Phase transitions occurred, like water freezing into ice, except these were transitions in the quantum fields themselves. The Higgs field underwent a phase transition, giving particles their masses. The electromagnetic and weak nuclear forces separated, which had been unified at higher energies. The strong nuclear force separated earlier still. Each of these transitions changed the nature of vacuum. The vacuum, when the universe was 1 second old, was different from the vacuum when it was 1 minute old, which was different from the vacuum today. We're living in a vacuum that has evolved. The nothingness we experience now is the result of cosmic evolution, of the universe cooling and fields settling into their current configurations. And the vacuum might still be evolving. Very slowly, on cosmological timescales, but evolving nonetheless. The vacuum of the far future might be different from today's vacuum. Not because of anything actively happening, but because the natural evolution of the universe changes the baseline state of space itself. The nothingness is dynamic. It has a history. It has a future. It's not static emptiness, but evolving emptiness, changing along with everything else in the cosmos. Let's connect vacuum fluctuations to black holes through Hawking radiation. Stephen Hawking showed in 1974 that black holes aren't perfectly black. They emit radiation due to quantum effects near the event horizon. Here's how it works. Virtual particle pairs constantly pop into existence near the event horizon. Normally, these pairs annihilate each other almost instantly. But if one particle falls into the black hole while the other escapes, the escaping particle becomes real radiation. The black hole loses a tiny bit of mass in the process. This is Hawking radiation. and it's powered by vacuum fluctuations. The vacuum's quantum foam is creating particles, and the extreme environment near a black hole's event horizon is separating the particle pairs before they can annihilate. Over immense timescales, this causes black holes to evaporate. A stellar mass black hole would take roughly 10 to the 67th years to evaporate completely. Supermassive black holes take even longer. But eventually, through this process powered by the vacuum itself, all black holes will disappear. When they do, they'll release all their mass energy back into the universe as radiation. The information that fell into them over their lifetime might be encoded in this radiation somehow. We're not sure. It's called the black hole information paradox, and it remains unsolved. But the key point is this: the vacuum is actively destroying black holes. Slowly, incredibly slowly, but actively. The quantum fluctuations in nothingness are eating away at the most extreme objects in the universe. Even black holes, the ultimate manifestation of gravitational power, are temporary structures. They'll all eventually evaporate back into the vacuum they arose from. The nothingness is patient. It can wait billions upon billions upon billions of years, but eventually it reclaims everything. Here's a wild idea that some physicists take seriously. The vacuum might be performing computations. Quantum field theory describes vacuum as filled with quantum fields in constant fluctuation. These fluctuations can be thought of as information processing. Virtual particles popping in and out, quantum states evolving according to Schrödinger's equation, fields interacting with each other. In a sense, the vacuum is running quantum algorithms. Not deliberately, not with purpose, but as a consequence of how quantum mechanics works. Every interaction between particles, every quantum fluctuation, is a computation happening in the fabric of reality. If you think of the universe as a quantum computer, the vacuum is the hardware. The quantum fields are the circuits, particles are the output, and the program is the laws of physics. This isn't just metaphor. Actual quantum computers work by exploiting vacuum fluctuations and quantum field properties. When you run a quantum algorithm, you're using vacuum properties to perform calculations that classical computers struggle with. The vacuum might be computing at scales and speeds we can barely imagine. Every cubic centimeter of space might be processing more information per second than all human computers combined. What's it computing? Nothing in particular, just the evolution of quantum states according to physical laws. But the raw computational power available in vacuum is staggering. Let's step back and think about what vacuum really is at the most fundamental level. It's space-time itself. Not empty space sitting inside a container, not nothing with properties. Space-time is the container. It's the stage, the medium, the foundation of everything that exists. When we talk about vacuum, we're talking about the basic fabric of reality, the coordinate system in which events occur, the framework that makes cause and effect possible. Without space-time, without vacuum, there could be no movement, no change, no time passing. Think about what that means. The vacuum isn't just part of the universe. It is the universe in the most fundamental sense. Matter and energy are disturbances in this fabric, ripples and waves and knots in space-time itself. You aren't in space. You're part of space, a pattern in the fabric, a temporary configuration of the underlying medium. And this fabric can be stretched, compressed, warped, rippled. It's dynamic. It responds to matter and energy. It curves around massive objects, creating what we perceive as gravity. It expands as the universe grows. It vibrates when gravitational waves pass through. The vacuum is alive, in a sense. Not conscious, not intentional, but active. Always changing, always responding, always evolving. And here's something that should give you pause. We don't know what spacetime is made of. We can describe how it behaves mathematically. We can predict its response to matter and energy with incredible precision. But we don't know what it fundamentally is. Is it composed of something more fundamental? Is there a substrate beneath spacetime? Or is spacetime the most basic level of reality with nothing beneath it? Some theories, like loop quantum gravity, suggest spacetime might be quantized at the Planck scale, that at the smallest scales, spacetime comes in discrete units rather than being continuous. Space might have a grain to it, like pixels on a screen, too small to observe but fundamentally discrete. If true, the vacuum isn't smooth, it's grainy, made of tiny chunks of spacetime stitched together. And if you could somehow zoom in far enough, you'd see the individual quanta of space itself. Other theories suggest spacetime might be emergent, arising from something more fundamental. That space and time aren't basic ingredients, but consequences of deeper physics we don't yet understand. We're swimming in an ocean we don't comprehend. The water we're made of, the medium we exist in, might be far stranger than we currently imagine. Here's something peculiar. The vacuum is connected to why time flows in one direction. The second law of thermodynamics says entropy increases, disorder grows, heat flows from hot to cold, eggs break but don't spontaneously reassemble. Time has a direction, an arrow pointing from past to future. But the fundamental laws of physics don't have this arrow built in. At the quantum level, physical processes are time-symmetric. You could run them backwards and they'd still obey the laws of physics. So why does time flow forward? Why do we remember the past but not the future? Why can't we unbreak an egg? The answer seems to be related to the initial state of the universe. At the Big Bang, the universe was in an incredibly low entropy state. Everything was compressed, uniform, simple. As it expanded, entropy had room to increase, and it's been increasing ever since. But here's where vacuum comes in. The expansion of vacuum itself might be connected to the arrow of time. As vacuum expands, it creates more room for entropy to increase. More volume means more possible configurations of matter and energy. The vacuum's expansion might be what gives time its direction. Past is the direction toward less vacuum, higher density, lower entropy. Future is the direction toward more vacuum, lower density, higher entropy. You experience time flowing forward because the vacuum is expanding. If the universe were contracting instead toward a big crunch, would time flow backward? Would you remember the future and not the past? We don't know. But it's possible that your subjective experience of time is intimately connected to what the vacuum is doing. The directionality of time might not be a fundamental property of reality, but a consequence of vacuum dynamics. The nothingness around you might be the reason you age, the reason you can't undo mistakes, the reason the future is uncertain while the past is fixed. Let's return to isolation from a different angle. The vacuum doesn't just separate individuals. It might separate entire civilizations across epochs. Imagine a galactic civilization that arises, spreads across thousands of star systems, flourishes for millions of years, then declines and goes extinct. They might leave artifacts behind, megastructures, radio transmissions propagating through space, physical remnants on planets they colonized. Now imagine another civilization arising in the same region of the galaxy millions of years later. They find the artifacts, they detect the ancient transmissions, they discover evidence of their predecessors, but they never meet. The civilizations are separated by time, by millions of years of vacuum between when one existed and the other arose. The galaxy might be full of such ghost civilizations, not current neighbors but temporal neighbors. Civilizations separated by the vacuum of time rather than space. This is another form of the isolation problem. Even if intelligent life is common, even if our galaxy has hosted hundreds or thousands of civilizations, we might never encounter any of them. Not because they're too far away in space, but because they're too far away in time. The universe is 13.8 billion years old. If technological civilizations typically last 1 million years, there's only a tiny probability that two nearby civilizations would exist simultaneously. We might be surrounded by ruins and artifacts and evidence of previous civilizations. We just haven't found them yet. Or we've looked but couldn't recognize what we were seeing. How do you identify alien artifacts when you don't know what alien technology looks like? The vacuum creates temporal isolation as well as spatial. The gaps in time are as uncrossable as the gaps in space. Even if another civilization existed in our solar system 1 billion years ago, we'd have no way to communicate with them. They're gone, and we can't reach backward through time to make contact. The loneliness isn't just about distance. It's about being adrift in time, in a universe so old that civilizations can come and go without ever overlapping. Ships passing in not just the night, but in different nights, millions of years apart. After everything we've discussed, we need to revisit our initial question. What is vacuum? We started by saying it's nothingness, emptiness, the absence of stuff. But we've learned that's wrong. The vacuum is filled with quantum fields, with dark energy, with dark matter, with virtual particles, with the potential for anything to exist, just waiting for the right circumstances. The vacuum has temperature, energy density, pressure. It can be warped, rippled, polarized. It mediates forces, enables particles to have mass, determines the speed of light. The vacuum isn't nothing. It might be the most something thing there is, the foundation of reality, the baseline state from which everything else emerges. Perhaps we've been thinking about it backwards. Perhaps the vacuum isn't the absence of stuff. Perhaps stuff is the disturbance of vacuum. Matter and energy aren't things in a container. They're ripples in the container itself. You aren't surrounded by vacuum. You're a pattern in the vacuum, a wave in the ocean of space, a disturbance in the fabric of reality. And when you die, when the pattern dissolves, you don't disappear into nothing. You return to the vacuum you always were part of. The atoms disperse, the energy radiates away, the pattern fades, but nothing is lost. The vacuum remains, slightly changed by your existence, but fundamentally unchanged. In a sense, you're immortal. Not your pattern, not your consciousness, but the substrate you're made of. The vacuum that temporarily configured itself into you will exist forever, rearranging itself into new patterns, new configurations, never truly creating or destroying anything, but endlessly transforming. The vacuum is eternal. You are temporary. But you and the vacuum are made of the same thing. You are the vacuum, briefly aware of itself. We've explored the vacuum from every angle we can think of. Its properties, its effects, its history, its future. But we're left with the same question we started with. Why? Why does vacuum exist? Why does it have the properties it does? Why quantum fields? Why dark energy? Why these specific laws of physics and not different ones? Science can tell us how the vacuum behaves. Physics can describe its properties with mathematical precision, but science can't tell us why. Why this universe instead of a different one? Why anything at all? Maybe there's no why. Maybe vacuum just exists, and asking for deeper explanation is like asking what's north of the North Pole, a category error, a question that seems meaningful but actually isn't. Or maybe there is a why, but it's forever beyond our ability to understand. Maybe the human mind, evolved to hunt and gather on an African savanna, simply isn't equipped to comprehend the deepest truths about reality. Or maybe we'll figure it out eventually. Maybe there's a theory of everything waiting to be discovered that will explain why vacuum has the properties it does, why this universe, why something rather than nothing. But even if we find that theory, it will probably just push the question back another level. Why those laws instead of different ones? Why mathematics? Why logic? Why anything? The vacuum might be pointing us toward questions that have no answers. Not because we're not smart enough, but because the questions themselves might be meaningless or unanswerable in principle. And maybe that's okay. Maybe the mystery is part of the beauty. Maybe not knowing why the vacuum exists, why we exist, what it all means, is what makes existence precious. If we knew all the answers, if reality were fully explained and comprehended, would it be as wondrous? The vacuum keeps its secrets. And perhaps that's as it should be. Before we finish, let me leave you with one last perspective on the vacuum's immensity. If you took all the atoms in your body and spread them out evenly through the observable universe, each atom would be separated from its nearest neighbor by approximately 10,000 miles. That's how much nothingness there is compared to the amount of matter. Or, think of it this way. If the sun were the size of a period at the end of a sentence, the nearest star would be about 10 miles away. And in between? Nothing. Just vacuum for 10 miles. Scale that up. If the Milky Way were the size of North America, the Andromeda Galaxy would be about the size of South America, and it would be located roughly where South America actually is. The space between them? An ocean of vacuum. Now imagine shrinking yourself down to quantum scales. You're the size of an electron looking at an atom. The nucleus is so far away, it's like looking at a star light years distant. And you're floating in that enormous gap, that quantum vacuum, where virtual particles flash in and out of existence around you. The scale of vacuum is incomprehensible from any perspective. Too large at cosmic scales, too small at quantum scales. And at every scale, from the tiniest to the largest, it's fundamentally the same thing. Spacetime, quantum fields, the fabric of reality. You exist at a middle scale, where the vacuum seems invisible and inert. But zoom in or zoom out, and you see it for what it really is. The dominant feature of reality, the ocean in which rare islands of matter briefly appear before dissolving back into the depths. Everything you can see, everything you can touch, everything that seems solid and real, is a tiny exception in an incomprehensibly large expanse of almost nothing. We live in the gaps between the nothingness, on borrowed time, in a universe that is overwhelmingly, undeniably barren. Let me briefly touch on string theory, because it has interesting implications for vacuum. String theory proposes that fundamental particles aren't point-like, they're tiny, vibrating strings. Different vibration patterns produce different particles. An electron is one vibration pattern. A quark is another. Photons are another. And these strings vibrate in what? Vacuum. Or more precisely, they vibrate through higher dimensional space that we can't perceive directly. String theory requires extra dimensions beyond the three spatial dimensions and one time dimension we experience. These extra dimensions might be tiny, curled up smaller than atoms, or they might be large but inaccessible to us somehow. The vacuum in string theory is more complex than in standard physics. It's not just empty space with quantum fields. It's higher dimensional space, with intricate geometry filled with vibrating strings and other exotic objects called branes. Different configurations of these extra dimensions produce different vacuum states. Each configuration has different properties, different fundamental constants, different physical laws. This leads to the landscape problem. There might be 10 to the 500 different possible vacuum configurations in string theory. Each would produce a different universe with different physics. Our universe might be one random configuration among countless possibilities. The vacuum we experience might be just one solution among an unimaginably large number of solutions to the equations of string theory. If this is correct, then asking, why does vacuum have the properties it does, might be like asking, why is Earth exactly 93 million miles from the Sun? It just is. Random chance. One possibility among many that happen to produce a universe where observers like us could arise. The vacuum might be fundamentally arbitrary. Its properties might have no deeper explanation than random selection from an enormous landscape of possibilities. Let's confront the deepest question, head on. Why does anything exist instead of nothing? This is philosophy meeting physics at its most fundamental, and the vacuum is at the heart of it. Some physicists, like Lawrence Krauss, argue that the universe could have arisen from nothing through quantum fluctuations, that the vacuum itself, with its quantum uncertainty, could produce a universe spontaneously. The idea goes like this. If you have a quantum vacuum, which isn't truly nothing but rather seething with quantum fluctuations, then given enough time, a large enough fluctuation could produce a universe. Our Big Bang might have been such a fluctuation. But this doesn't really solve the problem. It just pushes it back a step. If the universe arose from quantum vacuum, where did the quantum vacuum come from? Why does vacuum have quantum properties? Why are there laws of quantum mechanics at all? Other physicists argue that the total energy of the universe might be zero. Matter and radiation have positive energy, but gravitational potential energy is negative. If these exactly balance, then the universe as a whole has zero energy. A universe with zero total energy doesn't violate conservation laws by existing. It's a free lunch. But again, this doesn't fully answer the question. Why is there a universe with zero total energy instead of no universe at all? Why are there laws that permit zero-energy universes? The vacuum forces us to confront these questions because it's the boundary between something and nothing. It's almost nothing, but not quite. It's the minimal state of existence, the baseline. Some philosophers argue that true nothingness is actually impossible, that the concept of absolute nothing is incoherent. If there's no space, no time, no physical laws, then in what sense can we even talk about it? Nothingness can't exist because existence requires at least the framework of logic and the passage of time. Maybe the vacuum is what you get when you try to have nothing but can't quite achieve it. The minimal state of being that's logically possible. You can't have less than vacuum without having incoherent nothingness. Or maybe the vacuum is eternal. Maybe it never came into existence because it always existed. Maybe the question, where did vacuum come from, is meaningless. Like asking, what's north of the North Pole? We don't know. This is the edge of human knowledge, the boundary where physics meets metaphysics, where science meets philosophy, where our ability to understand reality hits its limits. The vacuum keeps its deepest secrets. We can measure it, study it, describe its properties. But the fundamental question of why there's something rather than nothing remains unanswered, maybe unanswerable. All we know is that there is vacuum. It exists. We exist within it. And that's both the most obvious fact and the most profound mystery. Let's discuss an important point. Life as we know it cannot exist in vacuum. But could life exist in other forms? On Earth, life requires several things. Liquid water as a solvent, energy gradients to power metabolism, complex chemistry to store information and perform functions. All of this requires an environment that vacuum simply doesn't provide. But Earth's environment isn't the only possible environment for life. Scientists speculate about other possibilities. Silicon-based life instead of carbon-based. Life using liquid methane as a solvent instead of water. Life on planets so different from Earth that we barely recognize them as habitable. Could there be life adapted to vacuum itself? Probably not. Even the most extreme forms of life we can imagine need some environment, some medium for chemistry to occur. Pure vacuum doesn't provide that. But here's a thought. What if advanced civilizations develop technology that lets them survive in vacuum? Not biological life, but artificial intelligence. Self-replicating machines that don't need air or water or warmth. That can function in the cold darkness of space. Such beings could spread through the vacuum of space in ways biological life never could. They could drift between stars on journeys lasting millions of years, inactive during transit, activating when they reach their destination. They could exist in environments that would kill biological life instantly, on the surface of neutron stars, in orbit around black holes, in the coldest depths of intergalactic space. If such artificial life exists, the vacuum isn't a barrier to it. It's a habitat. The nothingness becomes livable through technology. We might evolve in that direction ourselves, uploading consciousness into machines, spreading through the solar system and beyond as digital entities that don't require biology's fragile environmental needs. If so, the vacuum would cease to be hostile. It would become our home. We'd adapt to the nothingness, not by changing our bodies, but by abandoning bodies entirely. This is speculation, of course. We don't know if consciousness can be uploaded. We don't know if we'll survive long enough to develop such technology. We don't know if we'd still be us in any meaningful sense after such a transformation. But it's possible. And if it happens, then life won't be confined to rare islands like Earth. It could spread throughout the vacuum, making the nothingness less empty. Not filling it, the universe is too vast for that, but at least inhabiting it. The vacuum might not remain permanently lifeless. Given enough time and sufficient technological development, intelligence might learn to thrive there. The nothingness might become populated with minds that have transcended biology. And those minds would look back at Earth, at the wet, warm planet where life began, and marvel at how far they'd come. From a tiny oasis in the vacuum to beings that call the vacuum home. Here's a final troubling thought. Is our vacuum special, or is it typical? If the multiverse hypothesis is correct, and countless other universes exist with different vacuum properties, different fundamental constants, different physical laws, then our vacuum is just one possibility among infinite variations. Most of those other vacuums might be hostile to complexity. Maybe the fundamental forces are too strong or too weak for atoms to form. Maybe dark energy is so strong it prevents galaxies from forming. Our vacuum, with its specific properties that permit structure, formation, and life, would be incredibly rare, special, an anomaly. But that means we can't generalize from our observations. The vacuum we observe might not be representative of vacuums in general. It might be a weird outlier that happens to permit observers like us. Alternatively, if the multiverse doesn't exist, if ours is the only universe, then our vacuum isn't special. It's unique. It's the only one. But that raises the question of why this particular set of vacuum properties. Why these specific values for fundamental constants? Either our vacuum is one among infinite possibilities and we happen to exist in a rare habitable one, or it's the only one, and we have no explanation for why it has the properties it does. Either way, the vacuum we inhabit might be far from typical. We're studying a sample size of one and trying to extract universal truths from it. Before we conclude, let's discuss something hopeful. Despite everything we've said about the hostile nature of vacuum, humans have been venturing into it. It started small. In 1961, Yuri Gagarin became the first human in space, orbiting Earth for 108 minutes. He looked down at our planet from the vacuum and saw it whole, the blue marble floating in blackness. Then we went to the moon. Between 1969 and 1972, 12 humans walked on another world. They stood on the lunar surface and looked up at Earth, seeing our planet as a distant blue and white sphere hanging in space's blackness. They were standing in a place with no atmosphere, no protection from vacuum, held to the surface only by the moon's weak gravity. The Apollo astronauts experienced the vacuum in ways few humans ever have. During their 3-day journey to the moon and back, they traveled through it continuously, surrounded by nothingness, one small spacecraft, 3 humans, a thin metal shell separating them from death by decompression. And yet they went. They chose to venture into that hostile environment because they wanted to explore, to discover, to push human experience's boundaries. Since then, we've sent people to live in space for extended periods. The International Space Station has been continuously occupied since November 2000. People have lived there for months at a time, residing in a small metal structure orbiting Earth, with only millimeters of hull between them and vacuum. We're planning to go farther, back to the moon, then Mars. Each journey takes us deeper into the nothingness, farther from Earth's atmospheric and magnetic protection. A Mars journey will require 6 to 9 months each way. Astronauts will spend over a year crossing vacuum, tens of millions of miles from home, unable to turn back. They'll be more isolated than any humans in history. And if we ever want to reach other stars, the challenges become nearly insurmountable. With our current fastest spacecraft, reaching the nearest star would require over 6,000 years. Maybe we'll never achieve interstellar travel. Maybe the distances are too vast. Maybe we're confined to our solar system forever, gazing up at stars we can never reach. But we're going to try anyway. That's what humans do. We see the impossible and attempt it. We look at the nothingness and don't just study it from safety. We venture into it. Every satellite we launch, every space station we build, every probe we send to distant worlds represents an act of defiance against the vacuum. We're saying, you might be vast and hostile and incomprehensible, but we're going to explore you anyway. The vacuum doesn't care. It will persist long after we're gone. But we care. And that makes all the difference. In 1990, Voyager 1, approximately 4 billion miles from Earth, turned its camera around and photographed our planet. At Carl Sagan's request, it captured Earth from that enormous distance. In the photograph, Earth appears as a tiny pale blue dot, barely visible, less than a pixel in size, suspended in a beam of scattered sunlight, surrounded by the blackness of vacuum. Carl Sagan wrote about this image. He said, "Look at that dot. That's here. That's home. That's us. Everyone you love, everyone you know, everyone you ever heard of, every human being who ever existed, lived their lives on that tiny mote of dust suspended in a sunbeam. Every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every saint and sinner in human history lived there. On that dot, all of human history. All our wars and conflicts, all our triumphs and tragedies, all our art and science and philosophy happened on that pale blue dot, and surrounding it, vacuum, vast, indifferent, uncaring. From Voyager's perspective, Earth was insignificant, a tiny speck in enormous nothingness. And from the universe's perspective, we're even more insignificant. The vacuum puts things in perspective. It shows us how small we are, how fragile, how temporary. It reminds us that everything we fight about occurs on a tiny rock in incomprehensibly vast nothingness. Yet that pale blue dot is where life exists, where consciousness resides, where meaning is created. The vacuum might be vast, but it's barren. The dot might be tiny, but it contains everything that matters, at least everything that matters to us. Sagan also said the image underscored our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, because it's the only home we've ever known. We're alone in the vacuum as far as we know. We haven't found anyone else. We might be the only conscious beings in a vast, barren universe. Or if others exist, they're so distant we might never know. What we have on Earth is precious. Life in a lifeless void. Consciousness in an unconscious universe. Warmth and light and sound in cold, dark silence. We should take better care of it. The vacuum doesn't care if we survive. The universe continues whether we're here or not. But we care. We should care. Because in all that nothingness, this pale blue dot is the only place we know where there's something rather than nothing. When we study the vacuum, when we measure it and try to understand it, we're not just learning about nothingness. We're learning about ourselves. The questions we ask are fundamentally human. Why is there something rather than nothing? What is the universe made of? Where did it come from? Where is it going? What's our place in all this? The universe doesn't ask these questions. It simply exists. The vacuum doesn't ponder its own existence. Only we do that. When we feel insignificant, contemplating the vastness, that's a human emotion. When we feel isolated by the distances between stars, that's human. When we're alarmed by the ultimate fate of everything, that unease is uniquely ours. The vacuum is a mirror. It shows us ourselves, our fears, our hopes, our need for meaning in a universe that provides none. The nothingness is unsettling not because of what it is, but because of what it represents to us. The unknown, the unknowable, the edge of our understanding and control. We're pattern-seeking creatures in a largely patternless universe. Social beings isolated on a tiny rock in an asocial void. We create meaning in a cosmos with no inherent meaning. We're finite beings contemplating infinity. Temporary beings contemplating eternity. The vacuum shows us our limitations, our smallness, our fragility, but it also shows us our strength, our curiosity, our courage, our determination to understand even when understanding is difficult or frightening. We look at billions of light years of nothingness, and we don't turn away. We build telescopes, we formulate theories, we send spacecraft into the vacuum to investigate. We want to know, even when knowing is uncomfortable. We've spent considerable time together exploring the vacuum. We've examined it from every angle, the quantum foam at the smallest scales, the immense separations between stars and galaxies, the cosmic voids, the expansion, dark energy, dark matter, the ultimate fate of everything. And yes, it's profoundly unsettling. The universe is overwhelmingly barren and becoming more so. Matter, energy, and life are rare exceptions, temporary departures from equilibrium in an ocean of nothingness. We're infinitesimal in a cosmos indifferent to our existence. But here's what I find remarkable. We're not merely in the vacuum, we're constructed from it. The gaps inside our atoms, the quantum energy permeating reality, the dark matter flowing through us. We're integral parts of the vacuum, not separate from it. And despite being composed primarily of structured nothingness, we exist, we think, we question, we explore. We've determined that we inhabit a universe that's mostly vacuum, and we're attempting to comprehend the implications. That's extraordinary. Consider what we've achieved. We determined that space is expanding by meticulously observing distant galaxies. We detected gravitational waves, ripples in vacuum itself, using instruments sensitive enough to measure changes smaller than atomic nuclei. We sent spacecraft beyond our solar system into interstellar space. We're searching for life on other worlds, hoping we're not the cosmos's only observers. We're resisting entropy with every breath, every thought, every structure we construct. Biology is defiance of disorder. Life is complexity, emerging from vacuum, organizing matter into patterns capable of maintaining themselves, reproducing, evolving into novel forms. And consciousness? That's vacuum becoming aware of itself. We're structured nothingness, complex enough to contemplate nothingness. The universe examining itself through us. This won't last. We've been honest about that. Heat death approaches. Eventually all stars will extinguish. All black holes will evaporate. All structure will dissolve. In 10 to the 100th years, nothing will remain but vacuum expanding eternally. But that's unimaginably distant future. A 1 followed by 100 zeros. A duration so vast that all of human history represents an infinitesimal fraction. We have time. Not infinite time, but substantial time. And in that time, we can accomplish things. Explore, learn, create, connect with each other. Make the vacuum slightly less barren temporarily. The universe doesn't care. The vacuum is indifferent to whether we exist, but we care. We're here, conscious, and we determine what matters to us, regardless of cosmic indifference. Yes, the vacuum is daunting. The scale, the isolation, the inevitability. We're minuscule specks in unfathomable vastness, separated by unbridgeable distances, heading toward total dissolution. That's disconcerting, but it's also beautiful. Against astronomical odds, in a universe overwhelmingly hostile to complexity and life, we exist. For a brief, brilliant moment in cosmic time, matter organized itself into forms capable of thought and emotion and wonder. We're temporary patterns in an ocean of nothingness. We're here briefly, then gone, and the vacuum continues unchanged. But while we're here, we matter, not cosmically, but to each other. And perhaps that's sufficient. So when you next look upward at the night sky, remember what you're observing. Vastness, cold, darkness, expanding nothingness, the vacuum between stars, between galaxies, the fundamental fabric of reality. But you're also observing light that traversed that vacuum to reach your eyes, stars that formed from diffuse gas clouds, galaxies bound by gravity resisting expansion, a universe that, despite being predominantly barren, contains wonder. The vacuum is alarming. But it's also the arena where everything occurs, the canvas where stars ignite, the silence that gives sound meaning, the darkness that makes light precious. We exist in the nothingness, as manifestations of the nothingness, constructed from the nothingness. And for this fleeting moment in cosmic duration, we're here to witness it, comprehend it, be awed by it. That's the narrative of the vacuum. It constitutes most of reality. It's what reality is becoming. It's unsettling in its scale and barrenness and indifference, but it's also our home. And while we persist here, the vacuum isn't entirely empty after all. Thank you for accompanying me through this exploration of nothingness. I hope it's provided fresh perspective on the regions surrounding us, above us, within us. The vacuum is troubling, certainly, but it's our vacuum, and we're extracting maximum meaning from our time within it. Until we meet again, continue gazing upward at that beautiful, endless expanse. And remember that somewhere in that immense darkness, we're observing it in return, and that reciprocal observation makes all the difference.